Good afternoon, everyone. I'm a researcher at the Center for Quantum Computation and Communication Technology, and I'm going to talk to you about quantum computing in silicon. The classical computers that we all know and love rely on digital information. A classical bit of information can be either 1 or 0, corresponding to silicon transistor being switched on or off. The quantum analog of that would be a qubit, a quantum bit. The qubit can be represented by a vector, which can point in any direction, but it's always of the same length, so that all the states that a qubit can take can be represented on the surface of a sphere. Now, a qubit can be only measured in one direction, which means that the outcome of the measurement is always vector pointing up or vector pointing down. The simplest example of such qubit would be an electron spin. Electron is basically a very tiny magnet, and when measured, it's always pointing either up or down. However, it can be prepared in any other state in what we call a superposition of pointing up and down, partially up, partially down. This means that a single quantum state can represent both classical 1 and classical 0 at the same time. And that's where the power of the quantum computation comes from. There are many different types of qubits, many physical platforms that can accommodate such two-level quantum mechanical system. Here at UNSW, we work with silicon spin qubits. The other promising platforms are superconducting loops, where a qubit is a current flowing clockwise and anti-clockwise at the same time, ion traps, using electronic states of ions suspended in vacuum, or nitrogen vacancies in diamond, using optical states. Here, for each platform, I have listed leading academic institutions as well as private companies like Google, Microsoft, IBM, or Intel, to show you that there really is a race, a technological race to build a quantum computer, and the winner is yet unknown. All of those platforms has demonstrated very good, very robust single qubits, and there are ongoing efforts to show strategy how to couple multiple qubits together in a scalable way. Here at UNSW, we work with silicon spin qubits, and we hope that as soon as you have basic building blocks, we can use the expertise of microelectronics industry to put billions of those qubits on a single silicon chip. A group of Professor Michel Simons here at UNSW has developed a very special fabrication technique to produce qubits in silicon with atomic precision. We start off with a silicon chip placed in ultra-high vacuum. The surface of silicon is then passivated with a single layer of hydrogen. We then approach with the tip of scanning tunneling microscope, and we can selectively desorb the hydrogen atoms. This way, we can write any desired pattern into this lithographic mask. The sample is then dosed with phosphine gas, which will only adsorb to those exposed regions of silicon. We then heat up the sample to incorporate phosphorus atoms into the silicon crystal lattice. And finally, we grow a protective epitaxial layer on top of that. Then outside the ultra-high vacuum, we use standard cleanroom processes to contact this silicon chip so that we can perform electrical measurements at cryogenic temperatures. I'm a second-year PhD student, and my project is to couple two qubits together using phosphorus atoms in silicon to perform conditional operations between the two qubits. Such two-qubit gate would be a basic building block of universal quantum computer, like a transistor for a classical computer. And this is the device design that I'm using for that. What you're looking at is a micrograph of a silicon surface. The gray regions represent the hydrogen mask, and the orange regions represent the exposed surface of silicon. A structure in the middle, SET, is a single electron transistor, which is a sensor for our qubits. If we zoom into the central region, we can see the very top bit of the sensor, as well as two quantum dots which accommodate the 2 qubits. If we zoom in further into those lithographic openings, we can actually determine the exact atomic size of those lithographic patches, and thus the number of phosphorus donors that can be incorporated into those openings. In this particular case, we have 2 phosphorus atoms being accommodated in the left qubit and a single atom in the right one. So we use atomically precise lithography to engineer coupling strengths between the 2 qubits. Okay, but that's just 2 qubits. We need many more. And that's the proposed strategy, which allows for parallel and synchronized operation of multiple qubits in silicon. This is a 3-dimensional structure where a grid array of donors and sensors is sandwiched in between 2 vertically separated layers of control wires. On the right-hand side, you can see the actual scanning dynamic micrograph of this middle layer containing qubits and sensors. And we are currently developing multi-layer lithographic techniques. Okay, let's take a step back. Why do we actually need a quantum computer? Let me give you an example of a problem that classical computer really struggles with. It's called a traveling salesman problem. Okay? We have a salesman who wants to visit a number of cities, taking the shortest route possible. He knows all the distances between the 2 cities, between every 2 nodes, but he still needs to check all possible configurations, all combinations, to find this shortest path. And this appears to be one of those exponentially hard problems for a classical computer and simply takes a very long time to compute. While quantum computer can access multiple possibilities at the same time and find the answer very quickly. Similar optimization problems and search problems exist across various fields of technology that could potentially benefit from quantum computing in one way or another. But to be honest, we don't know the best application of quantum computer. We need to build one to really find out. All of those disciplines have well-developed mathematical algorithms that take advantage of parallel operation of a quantum computer. So the quantum software is already out there, and now it's time for quantum hardware to finally catch up. Thank you.